metric in the curvature with all of the open test.就是用那个方方的方法的证明。以后这个Grove Carson Grove 跟 Steven 要 observe 基本上同样的 argument， 它所有的 sphere shell sphere 都有。所以有 character 当然有明白。现在一个 interest 的问题就是讲，solid sphere 里面有什么 special 的 structure。首先我们讲的这个 solid sphere 分几种，第一，这个 S 5号的 S。So, it's a solid sphere, the first class. Those sphere cannot be written as a boundary of a sphere level. This is spin boundary. So this is very exotic. This kind of manifold can be characterized by so-called the KO characteristic number. What you will see. Corresponding to the mod2 index of the last spinner for the boundary method for any cell turns out. So sometimes called alpha invariant. This turns out to be, in part, it does not bound, it does not admit metric with scalar character of. I think about that. So a subsphere does not bound it, which do not bound a spin manifold cannot have a vector force character. And later, by the surgery result, the Richard and I do, also positive, but remove also the mistake. That is actually human. If it admits a metric with positive scalar curvature, then you cannot bound a spin manifold. The converse comes from the surgery argument. Because it turns out positive scalar character survive under spin covolution. And you can look at what kind of manifold you can spin covolution. So this is what settles the problem, at least for scalar character. So unless you get a metric which is not related to positive character, but of course you can still ask whether this manifold at least unsymmetric or not. Unsymmetric with which character that we still don't know. Now the second class of manifold are manifold that is not the boundary of pairwise momentum. And yet, it is boundary spin manifold. So it is not in this class, but in between manifold. These are spheres, all we are talking about spheres. Those which the boundary of a parallelism means tangent distributed. And so this is the manifold of interest. And now, before I go into that, we look at the first class first. M, which is the boundary of parallelism manifold. So these are a large class of manifold which have this matrix with positive dispersion. So those which this which the boundary of parallelism manifold, they actually have this metric positive which occurs. We're going to talk about this. So there's some construct of this, and I think we're going to prove they're affecting the Witt-Einstein metric. Also the Witt-Einstein metric. Because there's some problem that we need to solve, but I think we should expect the answer. So that this matrix normally has positive integration of Einstein. And in fact, they have some content structure associated with it. Compatible with content structure. So there are infinite number of content structure on this manifold where the matrix will be compatible with this content structure. So we call this structure called Sasaki structure, which I shall discuss. So there are some called Sasaki structure. Now, in between those which is the boundary statement was for at least in a metric positive scaling version, and yet it is not quite boundary parallelism manifold. It's kind of interesting. I'm not sure if the necessary sufficient condition. That means if you have metric positive basic curvature, that implies it's the boundary of the parallelism. One knows one side. I believe it may be true. So the question is, if a solid sphere emits a metric positive basic curvature, whether you will automatically boundary or some parallelism. It's not quite easy here is because the surgery actually works in this class of manifold. Then you can do surgery. But here we don't have a surgery for manifold positive. Although one can try, but not quite successful. Okay. Now, on the other hand, there is, to prove this one, there are two constructions. So let me mention. One is due to diagonal. One is the paper that I'm going to talk about for you. Now you see. So there are two constructions of this kind of method. One is using some attribute or common. So this is kind of we talk about it later, but public construction. So suppose you have a private bundle. The boundary of the private bundle could be our sphere. That is Müller sphere. The Müller sphere, S7, is boundary of some S3 this bundle over S4. Okay. Boundary of that give rise to electronic sphere. Okay. Now, you can suppose there's several values of this type. You can pop them together in the following way. You try to put this into here. And this one go upside down. So this one go up with this one, and you take the problem. It's no problem. So two fiber bundles, just like this. This goes for the this here. And this is the big sphere. So this is another big sphere, and then the pocket, there's the pocket here. That normal pocket, we draw it. Put it down there and draw them together. Well, of course, there's something around here, but I'm thinking the boundary of it. Okay? I'm thinking the boundary. So you get real sphere with it. So depending on the structure, how you do the plumbing, similar to the classification Lie group, etc. Lie group, E6, E7 and all that, you can construct all the manifold, all the sphere which bounds parallel manifold. According to Lewis. This is more common function. So what gives us is that you construct manifold possibility curvature on the basic thing first, and then you try to understand how to smooth up. So this is an interesting construction which I will talk about it sometime. So given two basic manifold, each of them possibility curvature, you see how to match them together to form a new manifold with possibility curvature. So of course you don't have to apply to a solid sphere, you can apply it to more general smooth manifold. So it's like a normal crossing construction in the geometry. Okay? And Sasaki-Einstein manifold was used by Boyer. So this reduced to motion pair in prison construction. So this is what I'm going to talk about today. But in between, this number 2 is kind of interesting to understand what is in between. To go to transformation for the sphere curvature, and yet it doesn't quite follow the Einstein metric. Of course, once you have reported scalar curvature, you can also make it to be constant scalar curvature according to the Yamaha problem. But there seems to me, there wants to mean there's somewhere more than that, because it's between scalar, somewhere between scalar curvature positive and rigid curvature positive. So this set, this gap, what kind of manifold do we expect to have that option? Of course, you can say that they're observation character in the matrix, and you, instead of saying that someone, lambda I are positive, well, of course, which means every guy is positive, and scalar character means that some of them is also positive, but you could have several of them positive instead. So I'm not sure what is the best statement that one could do. But these are just speculations. But the important thing is to get a construction kind of in between the surgery argument here, which makes everyone work, and kind of something in between this kind of construction on the plumbing. Hopefully, we can understand the solid sphere better. I'm not expert on solid sphere. Presumably, one can try to look at the topology of the solid sphere, see what kind of construction we could have on this kind of principle. Well, the solid sphere is well understood, especially the Carrier problem was solved by our faculty, Hopkins. So maybe one understands that now. I'm not so sure, but it's still an interesting question. So understand number 2. What's happening number 2? Okay, let's look at a solid sphere, which is bounded in our numerical first. So, Carrier Newton, famous work. This in 1963, I think. One of the papers that start out the important field of surgery, simple contact surgery. So these manifolds are called P, BP. P means pairizable, and Pn plus 1. So this is a subgroup of, they call it, this is group of solid sphere. The group of solid sphere are formed by taking connection. So those which bound pairizable manifold, they prove the following thing, that B P2m plus 1 equals 0 for m bigger than 1. We are all assume dimension bigger than 5 because a solid sphere are not understood for dimension 4. So all the time we assume this bigger than 5. So there's no solid sphere which bounds pairizable manifold with 2m plus 1. And B2m plus 2 equals 0 or C2 and is equal to C2 if 4m plus 2 is equal, is not equal to 2m minus 2 for some I bigger than 2. So 4m plus 1 is nothing, 2m plus 1 is odd number, is 0. But even number, the boundary manifold is equal 0 or C2. And it's equal to D2 if this is true. Now for 4m plus 2 equal to 2 to the power I minus 2 was not known for a long time until recently, solved by 4m plus 2 equal to 2 to the power I minus 2. This is called the Carrier problem, and it was solved by Hopkins and his co-authors. think in that case, they prove that is equal to 0. But this is a better check. In that case, they settle this problem. They solve the Carrier problem saying that there's no exotic. The Carrier event is always equal to 1. I think this implies this statement is equal to 0. But I think equal to 0 is equal. I forgot which way it was. You can check in the original Carrier paper. So that's one of the reasons why the Carrier problem is so famous. And number 3, BP4M. So M is equal to 2. So these are odd dimensional manifolds bounded by even dimensional manifolds 4M. This guy has order equal to 2 to the power 2m minus 2, 2 to the 2m minus 1 minus 1, comes the numerator of 4em over m, where b is the m Bernoulli number. So, this all relates to the index, just the index calculation. So, of course, you remember exotic sphere was understood because of the famous photograph of Gisbert index of a even dimensional.
So, what is that numerator?
Numerator of this number. Somewhat divisible by m, or I mean you cancel it, reduce it. Okay. So for example, BP8. So these are the Müller spheres. You look at it. BP12 is equal to I92. BP16 is equal to 8128. So you can calculate all that by that. Do you know all that? So in fact, you can write down the way to write this. So in fact, the map, there's a map, Carrerian Müller map, from sigma to 1 over 8, the index of 4m sigma. What BP 4m? So, what is sigma is a exotic sphere, and you take a boundary, you write what? V4m sigma, which is pairizable, the tiny bundle of tribute. Tribute tiny bundle. That means you have top dimensional number of vector field. You know the index of it. You can call the index of a manifold boundary. There's something called normal additive field or signature. Okay. This is signature. Or is the signature. signature comes from pairing for even dimensional. The middle dimension homology, and you have a signature on the pairing on the middle dimension. Together. The H2M tensor H2M to H4M. Okay? That gives a natural Poincare pairing in the intersection. The intersection has a signature at the coordinate form. So the number of positive argument minus the number of negative argument. So signature. Now here the manifold boundary is really somewhat careful. Homology has to be careful. Okay? I'm thinking this like this. So you have to look at how to define a signature correctly, and you can identify signature. So you can look at the Newton's paper where he constructs the solid sphere. But the key is to understand the additive field of multiple. Anyway. So now, so this gives you a way to understand the group of this Willow sphere by looking at the signature. Okay, now let's see how it works. Now, turns out this works by Blitzcomb, which allows you to construct some of these more explicit. So let me tell you what Blitzcomb did. Okay. So this is the Blitzcomb sphere. So BP4M is the second group. It's generated by element that's called here. That's it. So we know the group is the second group with all the BPM and K generator. So this is a sphere. A solid sphere. So please go make the following construction. Okay. So he said, we define E0 6K minus 1 E1K C2 squared. Look at this complex hypersurface. So this is a complex hypersurface sitting in C3, in Cm. Okay. Sitting in C2M plus 1. So this is a nice hypersurface. Here's the singularity at the origin. So, at the origin. And you can take a sphere in the setting it, that's called length. So here's the sphere. So in other words, I take the intersection. So basically what I do is I take a sphere in the setting this hypersurface. And you get an odd-dimensional manifold. And this is a sphere, and that turns out to be a solid sphere. Okay? Oh, okay. So this element, so let's call this, give it a name. sigma k or m1. Okay? The intersection of this with this value turns out to be a homotopy sphere. You prove that in fact it bounds at periodical value. So this guy is the BP4M. The fact that the BP4M is not surprising. In fact, Miller himself wrote the paper. I don't know if Miller wrote the paper before this cone or after this. This is the thesis of this cone. In fact, let's see. This is in 1966. You will assume this? Right. So Biscoe's thesis was written under his book. Okay. So 1966 probably is certainly before Miller. Before Miller's book. Miller's book is 1968. Anyway, he proved that this is homotopy sphere, and you can prove the length constructed this way always bounds some periodical vector. Okay, there's something called Milnor vibration nowadays. Oh, okay. Milnor vibration, and so it's natural frame that it bound. And there's a signature which we can, so the signature is divisible by 8 always. So there's a natural thing that from the Milnor vibration you can find the bounding manifold, this is always divisible by 8. You can prove that whenever there's a completely determined this number for k, which can call minus 1 to the power of k, and k. So please conclude that this k determines this manifold if you want to. So that means from sigma k, so this k is this k. This k determines the manifold if you want to, if k is equivalent to each other. Mod is number. Okay. Then this implies a manifold is equal to 1. So in other words, this number k, mod dp4m determines if you multiply the manifold. So that's why all the manifolds which are periodical can be completely described by this construct. So this method is statement completion. So in particular, one knows the following statement. Being a sphere itself is already a remarkable fact, although it may not be dp1 with a sphere. You see, this is the length. The length models after the singularity. Topologically, the singularity is just a cone over this length. Okay? what that means is that this fellow is actually topologically manifold, not singular manifold, because the length over it is topological linear space. Okay. So that means in high dimension, which is different from complex one dimension, complex one dimension topology determines the structure, right? In the sense that if the singularity is non-trivial, then it's topologically non-trivial. Here it says that topologically it could be trivial, and yet it is a non-trivial singularity. Non-trivial singularity. Okay, but that's the other point that I'm talking right there. But anyway, so this is one of the reasons why this is constructed. In high dimension, the singularity cannot be determined by topology only. Okay, now, you can, of course, generalize this construction more. You can look at so these methods are important, as you can see. In fact, the cone itself, I mean, this hypersurface itself are interesting. This metaphor itself, we will come back to that later. We can discuss Calabi-Yau metaphor associated with such a construction later. So, this is the metaphor which I can compare by infinity. I can get compact manifold, I can resolve singularity at the origin, I get about singular manifold. And you can ask under what condition it becomes a Calabi-Yau manifold. So these are questions which should be studied later. We'll discuss how this K comes in and all that. This is an interesting statement. Anyway, let's generalize this statement a little bit more. Look at a complex singularity of this type. So let's look at the singularity at this type. And look at summation sigma I squared equal to 1 also itself. But now we have all this weight. So not that 2, 2, 2, 2. These two actually just stabilize the thing in a way. And doesn't change the essential feature of singularity. But now I get ACO to AM. Now this defines an interesting lattice point. Okay. Look at this lattice point. I can associate graph. Associate graph. Here. And this graph has n plus 1 vertices. Which each of the vertices I just call it ACO of AN. So ACO AN now I decide, instead of looking at the integer, just by convenience, using the same symbol, call it a vertex. So I get n plus 1 vertices. And I look at the following thing. I say AI and AJ can be joined by one edge, even only if the GCD of AI, AJ is bigger than 1. Which is common device between AI, AJ is bigger than 1. Then I join them by edge. Otherwise, we don't join it. Okay? So, of course, the graph could be disconnected because sometimes they don't have anything in common with the other guys. And let's see even to be the part of TA determined by even integers. So AI are integers also. I also look at the vertex. Over TA to be done. AI are integers, even integers, it belongs to here, this here, but also those which can connect to even integers will be there. Okay, so it's bigger than even integers because look at the connect component. Put them together. Okay, this form a graph, and this set, let's call it LA. This vector. So I'm going to tell you what this concludes. This concludes that LA is an integer, integral homology sphere. If and only if integral homology sphere is basically a homotopy sphere if the fundamental group is true. Because if the fundamental is trivial, if it's integer homology, then you know it's all the trip. That's the homology sphere. Homology is the seventh homology. So this concludes the following statement. Either GA contains at least two isolated points. So in this graph, if it contains at least two isolated points, then it's a homotopy sphere, or two, GA contains at least one isolated point. So if it contains at least two isolated points, then it's already an integral sphere. Otherwise, it contains one isolated point. And this set, this subgraph, has an odd number of vertices. Odd number of vertices. And also, for AI not equal to AJ, which belongs to C even, the greatest common divisor between AI and AJ is equal to 2. So they give me a complete description of under what condition the sphere is actually an integral sphere, this complex length. So for Brother-Channel, straight homogeneous polynomial, the length is considered to be a homology sphere if and only it goes for this pole. So this is a element also in the isopsphere also, if n is bigger than equal to 3. In this section of those conditions. Because the fundamental would be trivial for n bigger than equal to 3. And also, by the Müller Bayesian theorem, you can prove that this must be boundary of VP. VP okay. So you have a good description of this kind of method. Now, let's look at so of course the description of this is one of this. Now, so let's apply it to the following case. C naught P plus C1 squared plus C2M plus 1 squared equals 0, or P bigger equal 1. So let's look at, here I put the discharge Q, but you can put all the squares instead. And let's see how they apply those criteria. Well, the criteria turns out is the following. P is equal to plus minus 1 mod A. Let's call this sigma P. 4M plus 1. Call this one. This guy also summation CI squared equal 1. This manifold together is called sigma P 4M plus 1. If P is equal to this, turns out this guy is just standard sphere, diffeomorphic to standard sphere. And if I assume P of 4M plus 2 not equal to 2 power minus 2. This is the number occurs in the parabola sphere. And P not equal to plus minus 3 mod A. Then sigma P 4M plus 1 is the exotic, it's called exotic Chevreul sphere. Which belongs to BP 4M plus 2. This can be proved by some calculation of the invariance. Okay. So, for this dimension, with P sets like this, you get this exponent sphere. Exponent Chevreul sphere. Okay. Now, of course, this kind of links are interesting because they relate to complex geometry, but they're not unique. So we got these spheres, all these exotic spheres, some of the standard, this case is standard. They can bound some interesting singular hypersurface, complex hypersurface, but they're not unique. You may have more different polynomials. Here you could have deformed this polynomial into get the same sphere on the boundary. Okay? So, the many possibilities that you can do, for example, Blitzkopf, actually the later Blitzkopf and Hammond. He is a physicist, actually, who works in the calculation of physics. Intervals by period. You look at other hypersurface. Instead of 3, you look at 5. Same as before. So you get a manifold. And this manifold could be related to the previous one that we had. So let's call this sigma filter manifold. And turns out this manifold is, well, first of all, this K also has a K here. K. So sigma K filter is equal to sigma K pi filter, even only if 3K pi is equal to 3K mod BP 4M. So there are going to be different converse relations that we have upon it. Okay. some preliminary discussion how extraordinary sphere come up by looking at all this. Now let's try to describe how the metric with positive sphere curvature or antimetric appear on this extraordinary sphere. Okay. By using this kind of complex singularity. Okay. And as I said, the antimetric, we expect to be able to know how to do it. It's going to be more careful. But not done yet. So these are some of the Sasaki structures. On the odd arithmetic. So these are manifold model after Taylor manifold. For a long time I thought these are manifold, I just call it Taylor manifold. Well, it turns out it's not quite that simple. And more stuff in the end. So this is a metric content structure. With a metric structure and also a content structure. So on the odd arithmetic manifold. Okay. So this will apply to odd arithmetic manifold instead of even arithmetic. And here we have the following structure. As I said, we print this model after Taylor geometry. Basically, model after the cone, you want the cone over this odd arithmetic manifold. The cone itself should be Taylor. You want to model the structure like this. So you just imagine you have a similar to the previous parameter. You have a cone, you want this cone to be Taylor. And you see what kind of structure it is. Okay. So you have a cone, and you have D over dr, the radial direction. The radial direction, you can take a J operator, move this guy to the boundary on the length. So you get vector field there. And this is called Rip vector field. Okay. So this is a Killing field. So this guy will preserve the metric G. I declared as a metric, and now I declared as a vector field. The vector field J of D over dr coming from here. Okay. And now, and I have an almost complex, almost CR structure. On this manifold. So there's this first one, there's a 114 eta. So that eta, where E eta, the power n is not in the field. So that's the content structure. I postulate that it's the one form for eta. So eta max D eta, the power n is not 0. And the distribution given by it, okay, given by kernel of eta. Okay. So it's kind of similar to this picture. I think the complementarity of this J of D over dr that defines the distribution. And this distribution has a J structure there. So I would have a J structure. Well, first of all, the distribution bundle is an even dimensional bundle. Kernel eta is an even dimensional in one form. And And I want a symplectic form, omega, which is d eta. Omega is d eta. Together defines a symplectic vector bundle over the manifold. Okay. Kernel eta is a even dimensional subbundle of any bundle. And d eta restrict to it defines a symplectic pair because of this property. Okay. On the complementary eta, it is decimal rank. Okay. So it defines symplectic vector bundle, and I want to exist at the J almost complex structure. Almost complex structure. Almost complex structure. Which belongs to endomorphism of this D. It's a D bundle, it's a symplectic bundle, and I found a guy, J, which is on the endomorphism of this D. So J squared equal to minus I as before. J squared equal to minus identity. And also D eta, Jx, Jy, equal to D eta xy. So you extract the symplectic form, just like the Taylor geometry case. And d eta x jx should be positive. Okay. And we define gt. We define the metric. Once you have a symplectic form and a J structure, you define the metric automatically. It's just defined to be hjy. So given metric is equivalent to given J and vice versa through this equation. Given a metric, you divide J by this equation, or you have J, you divide metric. So that's why in these four fellows, I don't have a J. The J is divided by this. Okay. Now, I can extend J to a fellow which we call phi on the tangential of the manifold. I simply define phi to be equal to J on the distribution itself, and is equal, and phi theta to be equal to 0. So theta paired with eta is equal to 1. Theta is the random field going to the eta. So theta, eta, and I want phi acting on theta to be equal to 0. And we can extend the metric as it is would be G D plus eta tensor eta. This which amounts to this theta. On the distribution given by the symplectic vector bundle is this metric. The eta, theta will go orthogonal to it is given by eta and by eta. This whole setting is called the Sasaki-Einstein metric, or metric context structure. Okay. Now, if the almost complex structure on D is integrable, then we set the almost complex structure to be normal, and they call it Sasaki-Einstein structure. J integrable, then definition, the whole thing is a normal contact metric structure and frequency harmonic structure. So the whole thing is modeled after the cone, as I said. J of DODR is not theta. So theta is J DODR. So you can define it by declaring that the whole thing can be declared abstractly the odd dimension manifold. You get a metric on the odd dimension manifold. This is metric. And you add R on new coordinate with the manifold. Together, define a complex manifold. And you get a Taylor metric here. Basically, the whole thing is just series these days. So you will put a cone, a metric cone on the odd dimension manifold. You demand it to be Taylor manifold with a J structure. The J is defined this way. And the complex, the Taylor structure also. Okay? So this basically the same as Taylor geometry race. As long as you remember that's what you do. You require the cone way to be done. Okay, but in that case, we do have a vector field, theta, which is nowhere anything. And this vector field is defined as fully as a flow. It's called weak vector field. So flow of this weak vector field. It defines a foliation, sometimes it's called characteristic foliation. But in general, this flow need not be closed up. The Killing field, but Killing field need not be a circle, defined by a circle. If it defined by a circle, then really the whole thing is basically semi-Taylor geometry. So the odd dimension manifold has this flow. But it's a Killing field, so it cannot be too bad over the wall. It turns out all the orbits close up. Close up. If you close up the circle action, then you can look at the orbit space M and mark the circle. There's an orbital. The orbital. And this orbital is Taylor. It's a Taylor orbital. So it's become the Taylor manifold with singularity. And the singularity is like an orbital singularity. So basically the idea is, whatever we can do in Taylor geometry, basically we can do for such a manifold. Except you keep track of singularity. So for example, you construct Taylor dimension, all that you can do it here, no problem. And now, you can leave this whole thing to here by using a circle foundation. Just like what we did before. You have a fiber bundle, you can do it even higher dimension sometimes, but at least for circle it's much easier. You can leave the whole thing up here. So if this Taylor is done, then you can make it into the Einstein here. Because it's just a circle bundle. And you have a connection, everything just works. So this, I thought, would be just a trivial consequence of the Taylor geometry. But Einstein is more trivial than what I thought. Namely, the orbit did not close up. If the orbit does not close up, this creates more complicated because then you cannot quite take a circle action. The group will be non-compact, will be like a line. Well, it cannot be too bad. That's why the whole field is still very close to Taylor geometry. Namely, after all, it's a Killing field. This weak vector field, no matter what, comes from polar action. So it could be, there's some orbit may become dense on some, the closure of the orbit could become so the whole thing is embedded in the tori in some skewed way. So the orbit doesn't close up. But tori itself has closed off. Okay. So the question is how they secure. And this turns out to is possible to create some more non-trivial geometry like this. But still, well, the construction on my former professor James Park and some other guys has given interesting metric structure which realize which cannot be constructed dialectical of this. And so this kind of interesting. But I think those constructions should still come from Taylor geometry. We do it correctly. Because these are still Taylor geometry. Anyway, so let's see how this works. So as I said, if you just allow them to close up, there's nothing so much to say. So we do some deformation as before. So just like in the Taylor geometry, you can deform the symplectic form by suitable movement, the symplectic form, omega, move to omega plus dd bar, or some function. That gives you a deformity of the Taylor structure. So probably you can deform the J structure suitably too. So here we want to deform this context structure and all that too. Okay? So how do you deform the context structure? You deform one complex one form. You want to deform it so that eta t is eta plus eta t. And it has the property that theta 0 is 0, and the eta t, where the eta t, the power across 0 for all t. I want to specify the following conditions. Find t, the orthogonal that will come here. We want it to be equal to phi minus theta. This is that other vector field, the ring vector field. Check it that way. And write down d eta t identity times the phi t eta t times the eta t. Okay. And so we want to study how these strings deform. And this guy should have the property, this one form, x theta to the 0. So it's basic form. Theta is the vector field, the ring vector field. Okay, so you can deform the Sasaki structure in this way. And so this is a condition that we always want to hold on for.
So which vector field is not full?
No, we fix the root vector field. So we want to make sure this holds always. A delta T, match D A delta T to the power n not equal to Q. So this is condition that we want to impose always on the deformation signature.
That should be one. You got to find it.
Oh, you want to. Not even Q. Because I want this one to be always Fx and then say the equation. Okay. So these are called basic form. Okay. It turns out when you prove if this condition are imposed on the deformation, which is obviously we need to make an assumption, then you can always deform in such a form that the phi t looks like this and gt looks like that. That's what they term. This defines a continuous family of South structure. Now, what's the point about this? We want to make this deformation, and we shall define the homomorphic groups using the basic form and the basic structure, imitate what Taylor geometry tells. This becomes a little bit more lengthy, so I will do it next time. Basically, the whole thing is imitate what happens in Taylor geometry and try to build it. So at the end, what we want to do is to write down the Taylor-Einstein equation in the context version. And from there, you can prove the existence of Einstein structure. Now, of course, for the positive scalar character, we know there are obstructions on Taylor-Einstein manifold. Therefore, there's obstruction for submarine manifold. That's why we do not know every exotic sphere that we mention has an Einstein metric which has a context structure, like what we say here. So, but in the case of exotic sphere, presumably it's always true, but it's nice to figure it out in detail. But in the proof, there exists always a metric positive Ricci character. This is similar to the statement in Calabi conjecture, where first check class being positivity has no option. You can always make the Ricci character positive. So therefore, in the same token, you can prove these exotic sphere I just mentioned. Because, first of all, I wrote down all those polynomials, singular polynomials, is to produce context structure. And so they all have this context structure. So you can use this context structure to produce a metric positive character on the exotic sphere. But to make it to an Einstein takes some work that is not clear yet. Right? Except in some cases, we can prove that they are. I'll do it next time. So next time will be Monday. Monday and 10:30.